Welcome back, folks. We've talked about the horizontal scale. Horizontal's this way. We've talked about the horizontal scale of our sinusoids. We've talked about the vertical scale of our sinusoids. And then that third piece of information is how far we're going to shift it in time. Okay, so we're thinking shifting it along the horizontal axis, left to right. Hopefully we build on some of your knowledge of functions that you learned in maybe pre-calculus about how to shift functions, because we describe it a little differently when we're talking about phasors, but it's really the same concept. Okay, so I have a couple sinusoids plotted. Let's take a look at those. Okay, I have a blue one and an orange one, and if you're looking at the blue one, you notice that the positive peak is here at t equals 0. So I've written the function here for that sinusoid. It's got a magnitude of 2. Okay, you see it peaks up here at 2. Its negative peak is at -2. So it's a phasor that's 2 units long as it spins. Okay, I gave it an angular frequency of 2 pi radians per second, just so we get one full period in 1 second. It's just easy to look at. And then it has a phase shift of 0. Okay, when the phase shift is 0, I expect the positive peak to be right here at t equals 0. The orange waveform is shifted to the right a little bit, and I put a marker here on the positive peak so that we could see how far it's shifted. Okay, so right now we have the benefit of being able to place the marker exactly where I want it to be. And the reality is, if we're going to look at an oscilloscope, we're making a judgment. And we might place a cursor and we might be off by a little bit. And that's going to happen. I made sure that one's perfect, right where we want it. Okay, the orange one's shifted to the right. And what I'm hoping is that you remember back from pre-cal that when you shift a function to the right, what you end up doing is taking that function and copying everything, but then when it comes to the domain variable, so the domain variable in this case is t along the horizontal, you take t. I'm going to put a second set of brackets in here, right? And if I shift to the right, I subtract time, right? So I'm subtracting, and what am I subtracting? I'm subtracting 0.125. Okay, just like that. And by subtracting that time, I shift this whole function over by 0.125. Okay, but if you go back and you think about what I said in the previous videos, we talk about phase shift in terms of angles. Okay, so we have to understand how much time it takes to move a certain number of degrees or a certain number of radians. Okay, but if we write it this way and we plot it, we'll get this orange line. And to figure out the angle is really just a matter of taking this angular frequency and distributing it to both of these terms. So we can say 2 cosine 2 pi t, okay, and I'm going to subtract 2 pi times 0.125, okay, just like that. And if I look at this, I'm going to grab a calculator here, grab your favorite calculator, and we're going to find that this is 0.785 radians. I'm rounding a little bit because really what that's equal to is pi over, I want to make sure that I'm right. Yeah, pi over 4. Okay, so that's equal to pi over 4. And think back to what this is going to look like in degrees, or go convert it into degrees if you want. But that's equal to 45 degrees. Okay, so, but I got this negative sign out here, right? So let's write this all together. 2 cosine 2 pi t, and it's minus 45 degrees. The minus because we shifted to the right. If we shift to the left, then it's going to be a positive. But distribute that out and keep the sign, and you'll be okay. Okay, so that orange one is going to be 2 cosine 2 pi t, and we write it, as electrical engineers, we write it as negative 45 degrees. All right, something else that we do that might help us here is, let's see, I want to make some space so maybe I can pull off getting this all on the screen. So let me just slide that over behind my head. Something else we do is we draw what's called a phasor diagram. Okay, so the phasor diagram is really just looking at all the phasors that are interesting to us on the complex plane. Okay, so we have the real value or the real axis and the imaginary axis, and we know that this one is 2 at an angle of 0 degrees, and this one down here is 2 at an angle of negative 45 degrees. That's behind me. Ta-da! 2 at an angle of negative 45 degrees. Okay, so let's draw these roughly. Okay, and we have 2 at an angle of 0. So that's going to be here, right? 2 at an angle of 0. There's your first phasor. And then 2 at an angle of 45. So it's going to be the same distance, and it's just going to be at an angle of negative 45. Okay? These phasors are a snapshot of what's going on at t equals 0. So if I look at the distance from the tip back to the imaginary axis, okay, I can tell you that at t equals 0, the blue waveform is going to have a magnitude of 2. Okay, and it looks like that's the case up here. If I look at the orange phasor, I'm interested in this distance from the tip back to the imaginary axis, and that's going to have a magnitude that's a little less than 2, right? And we see that it looks like it's 1.4, give or take. Okay, so these phasors represent what's going on here. So that phase shift, negative 45, tells me where to draw that phasor. Now, as we set these rotating, we're going to rotate them counterclockwise, right? The 2 is going to head this way, so it's going to head towards 0. Okay, so it's at its peak and it's going to head towards 0. So the blue is here, it's at its peak, and it's going to head towards 0. This one's not at its peak yet. It's going to head towards its peak. Okay, so it's positive because it's on the right side of the imaginary axis. And as it spins counterclockwise, the first thing it's going to do is head towards its peak. And it's going to take 125 milliseconds to get there if it has an angular frequency of 2 pi. Okay, and it will go around and around. And we can talk about this as the phase shift between the angles. Okay, so right, this here, or the phase difference, is what we call the phase difference. All right, so this is phase shift, and it's really a shift in time, okay? But we usually don't talk about it as a shift in time. We talk about it as a shift in angle. How far does the phasor need to rotate to get back to 0? Okay, so here's negative 45. If it goes 45 degrees, it'll be at its peak. So we talk about this point as the 45-degree point. All right, bit strange. We're going to use it a lot, and we're going to draw enough phasor diagrams that I hope you become more comfortable with this concept. Okay, let's see. I got some drawings that I think might help us with that. Right. So hold on, let me get those out for you. All right, and we start with the phasor diagram on the left and the time domain function on the right. So if our phasor starts here at 0 degrees, so this looks like it's 1 at an angle of 0, we're interested in this distance, right, the horizontal distance back to the imaginary axis. And that's going to be drawn as the vertical distance along here. So here's our time axis, and here's the value of our function. Okay, so we'll discuss where the waveform is, or how much of the waveform has been drawn in terms of angles sometimes. All right, so if we go from that and we let it spin in time, we let it spin 45 degrees, Okay, we can see we're up here, and the distance from the tip back to the imaginary axis is now 0.707. A little bit of rounding there. And in that 45 degrees, we've traveled this far. So this is 45 degrees of one period. All right, keeping this party going, let it rotate another 45 degrees, and we should be at 90 degrees, right? And that's going to look like this. I'm going to run out of room if I keep doing this. Okay, so there's 90 degrees, right? So going from the peak to the first zero crossing, we sometimes talk about that as 90 degrees of our cosine. All right, speeding up a little, let's take a step of 90 degrees again. Phasor's going to be pointing out that way. Okay, and we've gone 180 degrees. So this is half of a rotation. We've gone from the positive peak all the way down to the negative peak. And you can see here we're talking about 180 degrees along our horizontal axis. All right, 90 degree step more, two more of these, right, to get all the way around. 90 degree step more, we're back to zero. It's right along the imaginary axis, and we've come back to zero, but now we're rotating the other way. So it's a positive going zero crossing. But we have 270 degrees of rotation. We started out here, whoops, we started out here, and we've gone 270 degrees. So that's 270 degrees of rotation. I'm going to slide that up there so I can get the last one in here. Last 90 degrees, and we're going to complete 360 degrees, and we get one full rotation, right? We've gone all the way around, and we're back here to our positive peak, and we see that we have 360 degrees along the horizontal axis. So we do this sometimes where we'll talk about the time if we're interested in the period, but if we're more interested just in how two waveforms relate to each other, we might talk about the distance they're shifted as an angular distance. Okay, and we call that angular distance the phase shift. Okay, so I'm going to try to get all of this in as much as I can for when I post this, but it is a bit cozy on this image. You'll get a nice long image for this one. All right, I hope you're getting more comfortable with this concept of when we shift in time, sometimes we talk about it in degrees and how to find it. Okay, we'll do some examples of this later on, but this is the third thing that we use to define a sinusoid. The amplitude gives us the horizontal. The frequency, the angular frequency gives us, did I do horizontal? The amplitude gives us the vertical stretch. The angular frequency gives us the horizontal stretch. And then the phase shift tells us how much we slide left and right. So these are the three parts of a sinusoid. Okay, there's some other values that are important that aren't part of the sinusoid, but we got to figure out how to shift up and down for starters, and some other things like that. So we're going to cover those in the next videos. Stay tuned and good luck.